How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're taking a look at understanding and working with the equilibrium constant. So our objectives will be to infer if an equilibrium lies far to the left or far to the right based on the magnitude of the equilibrium constant, as well as manipulate the equilibrium expression and determine the resulting values for KEQ. For example, if we were to flip an equilibrium around, or if we were to double the coefficients, or we were to combine equations, what's going to happen to that KEQ value? And I got some highlights here that we'll come back to. All right, so what does the magnitude of KEQ tell you about how big or how small? If it's really big, what's that tell you? If it's really small, what's that tell you? So we know that the KEQ is typically the products to the power of whatever they are, divided by the reactants to whatever the power they are from their coefficients. So it's products over reactants. So if KEQ is significantly bigger than 1, if it's a really big number, then the equilibrium lies to the right, meaning there are significantly more products than reactants at equilibrium. So here I have an equilibrium, here I have the value for its KEQ, and you can see it's times 10 to the 8 power. So this is a huge number. The way we get a huge number is by having a whole lot of products over a little bit of reactants. So we say that lies far to the right because we go reactants, products, which direction, which side are we leaning to? We're leaning to the right on the product side. If the value is really much smaller than 1, then the equilibrium lies to the left, which just means that there's a lot more reactants than there are products. So here's an example. Equilibrium with a KEQ value of 10 to the negative 30. So that negative exponent is telling me it's significantly smaller than 1. So I have something like this, where I have a tiny bit of products and a whole lot of reactants. So we describe that as lying to the left. All right, first little thing when we're messing around with things, the KEQ of the reverse equilibrium is the inverse of the forward equilibrium, or, put mathematically, the value for K for the reverse process is just 1 divided by the value for the forward process. So since equilibriums can be approached in either direction, you can either start with the left side or the right side and make the equilibrium. The way you write the equilibrium on paper determines which way the KEQ expression is written. So for example, here I got N2O4 in equilibrium with 2NO2. Now I can look at it this way, or I can look at it this way. And it's the same equilibrium, but we wrote it differently, so our KEQ expression is going to be different, right? So the expressions are going to be the inverse of each other. Here I wrote N2O4 on the left side, so it's going to be on the reactant, so it's going to be on the bottom of my KEQ expression. And I end up with this value. But if I were to write it the other way, which would be the same equilibrium, I didn't actually change anything except how I wrote it. Well, now my KEQ expression is going to be different. It's going to be flipped, which means that the value I get is also going to be different. It's going to be the reciprocal. So basically, if I flip it around, I got to take the reciprocal of one to get the other. All right, so that's the first little tidbit. Here's some practice. The following equilibrium has a KEQ of that number. Here it is. What is the value for KEQ for this equilibrium at the same temperature? Oh, hey, well, what's the difference here? All I did was flip my the way I wrote it. So my new KEQ, I'm going to call that 2, is going to equal to 1 divided by the original KEQ because I flipped it. So it's really equal to 1 divided by 1.24 times 10 to the positive 2, which when I plug and chug, beep, bop, boop, 0.00806. So that would be the answer to that kind of question. All right, second little tidbit. The equilibrium constant expression of a reaction that has been multiplied by a number is the KEQ raised to the power of that number. So for example, this is really showing the same equilibrium again, N2O4 in equilibrium with 2NO2, but I could go, hey, I want to double all of this. Maybe I'm doing some Hess's law kind of stuff, and I double the whole thing, and I end up with this equilibrium instead. Well, what do I have to do to that KEQ value to get the new one? Well, I change the coefficients, which means I'm going to change the exponents of my KEQ expression, right? So For the first, how it was written originally, it's the pressure of NO2 squared divided by the pressure of N2O4. Now, my second KEQ is a little bit different. Hey, the coefficients have changed, so have my exponents, right? It went from 1 to 2, or 1 and 2 to 2 and 4. So how do I go from this to that? Well, I just do the same, I double the exponents. So because the coefficients are doubled, so are the exponents. This effectively is squaring that KEQ. So the KEQ for 2 is the same thing as KEQ for the first process, but squared, right? If I were to triple it instead, I would raise it to the third power. Instead of KEQ being to the second, I would put it to the third. Whatever you do to the coefficients, you have to do to that exponent. All right. So yeah, that's the second little tidbit. Third little tidbit. The KEQ for a net reaction made of 2 or more steps is the product of the KEQ for those steps. Basically, if you add equilibriums together, you got to multiply their KEQs together. So here's an example. I got these 2 different equilibrium, and I can go, hey, I'm going to add these. I'm going to combine these together, right? So I look, hey, my BR2s cancel out, and I think that's the only thing that cancels out, and I end up with this resulting equilibrium when I combine them. Well, what is the value of that KEQ going to be? I know the values for the each step, but what do I got to do with them to get my new KEQ? Well, let's take a look at the expression. So for step A, the KEQ expression is going to be the concentration of NO squared times Br2 to the 1 divided by the NO-Br concentration squared. And then when I take a look at the B equilibrium, it's the same kind of process. Concentration of BrCl squared divided by concentration of Br2 times concentration of Cl2. And now, before I mess with things, let's write out what would the equilibrium constant expression be for the product, the resulting reaction. Well, it should be the concentration of BrCl squared times concentration of NO squared all over the concentration of NO-Br squared, because of, I'm looking here at those times concentration of Cl2. So how can I get this from these steps? Well, if I multiply them together, hey, look at this. The Br2 cancels out there, and I end up with, hey, exactly that expression. So if I want the values, I got to do the same thing to the values. I take 0.42 times 7.2, and I didn't do this math. It equals whatever the answer is, right? We don't really care too much about it. Probably going to be like 2 point something. All right, so summarizing. The KEQ of the reverse equilibrium is the inverse of the forward equilibrium, right? K for the reverse is 1 divided by K of the forward. The KEQ of a reaction that has been multiplied by a number is the KEQ raised to the power of that number. So whatever you multiply the equilibrium by, you got to put that KEQ value to the power of that number. And then if you have a net equilibrium from combining 2 or more steps, you got to multiply those KEQs together to get the KEQ of the resulting equilibrium. So yeah, summarize. Do you know what to do with these things? If the KEQ is really big or really small, what does that tell you? If you flip the equilibrium, what do you got to do to the KEQ? If you double it or triple it or cut it in half, what do you do to the KEQ? And if you combine multiple equilibriums, what do you got to do with those values to get the resulting equilibrium? All right, I hope you found that helpful. I'll see you in class. Goodbye.